All right, we'll go ahead and get started. Excuse me. We are doing lesson 8 today, and this is a continuation of talking about derivatives. In the last video, I talked about one way to get or define the derivative or change in value for a particular function. And we use the limit definition, part of the limit definition, that difference quotient. Well, today I want to show you some shortcuts on how to find derivatives and also introduce you to the main rules that you'll be using to find derivatives. Excuse me. So below is a list of all the differentiation rules that we're about to go over. The first one, if your function is a constant, then the first derivative is automatically 0. For example, if you had the function f of x equal to -5, well, its first derivative, because it's a constant, is automatically 0. The next one is something called the constant multiple rule, and it states if you have a constant in front of a function and you take the first derivative, then that constant is going to stay in front of your function. So that's what the constant multiple rule is. Power rule is a rule that you will be using a lot of when taking a derivative. Given your function f of x, or it could be g of x, or any other letter, equal to x raised to the n as in Nancy power, then to find the first derivative, it looks like you're pulling the original exponent to the front and multiplying it times whatever constant is there, and then you subtract 1 from the original exponent. For example, given f of x equal to -7x to the 6th power, and we need to find the first derivative, or f prime. Use the power rule by first moving your original exponent to the front and multiplying it by that -7. So that will give us -42. And the last step, you subtract 1 from the original exponent. So that would be -42 x to the 5th power. Let's look at another example. Given f of x is equal to 4x, we need to find the first derivative, or f prime. There's no exponent, but it's assumed to be to the first power. So using the power rule, you move the original exponent to the front, multiply it by that 4, which is still 4, and you subtract 1 from the original exponent. Now that gives us 4x to the 0 power. And y'all know that any non-zero base raised to the 0 power is automatically 1. So x to the 0 is 1. Our first derivative is actually positive 4. I won't go over the sum and difference rule because it's self-explanatory. The next one is the product rule. And let me screenshot this and put it on our whiteboard. And let me go over, let me share my whiteboard. Hold on. Product rule, if you have a function h of x equal to two different functions, f of x times g of x, pardon me, then to find the derivative, or h of x, you take the derivative of f, whatever it is, times just g of x, the original g, plus the original f of x times the derivative of g of x. So let's look at, let me see if I have an example. If not, I'll make one up. Let's look at this example. We have h of x equal to 2x plus 1, or 2x squared plus 1, times 8x cubed plus 4x squared. Because we have a product, let's use the product rule for derivatives. And our first function is f of x. Second function is g of x. Now let's use the product rule and write down everything. And the derivative of f, which is the derivative of 2x squared plus 1, times just g of x, that's the original g, plus the original f of x, or just 2x squared plus 1, times the derivative of g of x, or the derivative of 8x cubed plus 4x squared. Now, back to the front of the problem, the derivative of 1 is a constant, so according to our constant rule, the derivative of 1 is 0. The derivative of 2x squared, to find it, you just use the power rule for derivatives by moving your original exponent to the front and multiplying it by the 2 that's already there. So that would be 4. And don't forget to subtract 1 from the original exponent. So that would just be plain old x to the first power. Bring down g. Bring down f. And now we're ready to take the derivative of g of x. So use the power rule for both terms. Move the 3 in front and multiply it by the 8. So that would be 24. And subtract 1 from the original exponent. That will give you x squared. And then the derivative of 4x squared, when you use the power rule, that will give you, we'll move the 2 to the front and multiply it by that 4. And that gives you 8. And you subtract 1 from the original exponent, that gives you just x. Now, unless directed otherwise, you can leave your answer in this type of form. Let's look at another question or another function that involves a product. We have h of x equal to negative 3x times, in parentheses, 11x squared plus 5x minus 9. Take the first derivative. Now, I realize we can distribute the negative 3x and just use the power rule for each term, but let's assume we can't do that, and let's use the product rule instead. Your first function listed is your f of x. Second function is g of x. So let's bring down the product rule. And we'll fill in each component. All right, the derivative of f means we're taking the derivative of negative 3x to the first power times the original g plus the original f, and I can erase that plus sign since our original f is negative, times the derivative of g. Now, going back to the front of the problem, the derivative of negative 3x to the first power, using the power rule, we move the original exponent to the front and multiply it by the negative 3. So that would still give you negative 3. And you subtract 1 from the original exponent. That's x to the 0 power now. Times g, bring it down, plus, well, in this case, minus your original f, and times the derivative of g. 11x squared, we're using the power rule. So move the 2 to the front and multiply it by the 11. That's 22. And don't forget, subtract 1 from the original exponent. So that would just be 22x to the first power. Second term, you do the same power rule. Move the 1 to the front and multiply it by 5. So that will still give us 5. and subtract 1 from the original exponent. And that would be 0 for the exponent now. And the derivative of -9 is a constant, so using the constant rule for derivatives, that's 0. Now, x to the 0 power in both cases is 1. So I'm just going to erase this part here because that goes to 1. And do the same thing here at the end. Now, for this particular question, let's say the directions want you to multiply out. So let me make some room and we'll multiply out and get a final answer going. Distribute the -3, that gives us -33, x squared minus 15x plus 27. And when we distribute the -3x, we get -66 x squared minus 15x. Now, the last step, when we combine like terms, our final answer is -99x squared minus 30x plus 27. Now, your answer here is correct. You don't have to go any further, but if you did, I would count that right too. Namely, if you factored a 3 out of all 3 terms, then this factored answer is also acceptable. So that's how you use the product rule. What if you had to take the derivative of a fraction? Well, we have a rule for that also, called the quotient rule. Now, if you compare the product rule with the quotient rule, you don't have to remember much because the numerator in the quotient rule is practically the same as the product rule. The only difference is a subtraction sign. So let me introduce you to the quotient rule. Given a function h of x is equal to f of x over g of x, then to take the first derivative or find the first derivative, you do up top the derivative of f times the original g minus the original f of x times the derivative of g of x. And this part is new. This is all divided by your denominator quantity squared. So if you can remember the product rule, then you don't have to remember the numerator in the quotient rule. It's the same order, but a different sign in the middle. Let's look at an example. Given h of x is equal to 2 over x, we need to find the first derivative. Clearly, because we have a fraction, we use the quotient rule in which the numerator is f of x and the denominator is g of x. So let's plug everything in. We're taking the derivative of f, or derivative of 2, times the original g of x, which is just x, minus the original f, which is 2, times the derivative of g, or derivative of x, and that's all over g of x quantity squared, or just x squared. Now, going back to the front of our setup, the derivative of 2 is a constant, so we know the first derivative of any constant is 0. That entire first part of our setup goes to 0. To take the derivative of x, we use the power rule, and it's understood to be to the first power. Move the original exponent to the front, and subtract 1 from the original exponent. So that will give us x to the 0 power, which is equal to positive 1. So that derivative is equal to 1. So our final first derivative, this would be negative 2 all over x squared. Let's look at another fraction and find its first derivative. Give me 1 second to clean our whiteboard, okay? Second example, given h of x is equal to negative 3x over x plus 1, find the first derivative. Again, since we have a fraction, we must use the quotient rule. Identify f and g. Your numerator is f, and your denominator is g. And let's fill everything into our quotient rule. First up, f prime of x, or derivative of f, or derivative of negative 3x, times the original g of x, or x plus 1, minus the original f of x, which is negative 3x. Watch the double negatives there. Make sure your signs are correct. And then the last part here up top, times the derivative of g of x, or derivative of x plus 1. And that's all over your denominator quantity squared, or x plus 1 all squared. So far, we've seen enough of how the power rule works. So I'm just going to take the derivative without going through the steps this time. The derivative of negative 3x is just negative 3. The derivative of x, we saw that earlier, that was just 1. And last but not least, the derivative of 1, that's a constant. That's always 0. Now let's get everything put together. Up top, we have negative 3 times x plus 1. The double negatives change to a positive 3x. All over x plus 1 quantity squared. And for this problem, we can go a little bit further. The algebra is pretty easy. By distributing the negative 3, so that would give us negative 3x minus 3 plus 3x all over your denominator squared. Well, we can do one more thing, namely cancel out the 3x's. So our final first derivative, h prime of x, is negative 3 all over x plus 1 quantity squared. So that's how you use the quotient rule whenever you have a fraction. Let me show you the rare case in which the quotient rule would not be ideal to use. And that is with this kind of problem or fraction. If you had h of x equal to 7 over x, now we used the quotient rule with a similar fraction, but I'm going to show you a neat shortcut. We can rewrite our problem using a negative exponent or reciprocal. 7 over x to the first power is the same thing as 7x to the negative first power. You can use the power rule a lot easier than the quotient rule. So we'll move the original exponent to the front, multiply it by 7 to give us negative 7. And even with the negative exponent, you still subtract 1 from the original exponent. When we do that, we get x to the negative 2 power. All you have to do at this point is change the negative exponent back to a positive one, and you got your first derivative. So that would be negative 7 over x squared. Let's look at the next rule for derivatives. This is called the chain rule. And using composite functions from algebra, this is the chain rule, how to find the first derivative when you have to use this rule. Now, this part here means that if you have a function inside of a function, like a composite function, so to find the first derivative, you just take the derivative of the outside function. The inside function doesn't change, you just bring it down. And here's the chain part of the chain rule. Whatever your inside function is, your g of x, you take the derivative of that on the outside. Let's start with this problem. We have h of x equal to -5 times, in parentheses, x squared plus 1. And that x squared plus 1 is raised to the 10th power. And we need to find the first derivative. You actually use the power rule first whenever you have an exponent. So move the 10 to the front and multiply it by the -5. And that gives us -50. X squared plus 1 is your g of x. So according to the power rule, we just bring that g of x down or over. Now, this part of the chain rule says now take the derivative of g. All right, so we'll take the derivative of x squared plus 1. Derivative of x squared, when you use the power rule, that's just 2x. And the derivative of 1 is a constant, so it's automatically 0. Now, when we multiply 2x by -50, we get our final first derivative of -100x times x squared plus 1. Let's look at a problem that has a fraction raised to an exponent. Given h of x is equal to, in parentheses, 3 over 7x minus 2, all raised to the 8th power. We need to find the first derivative. Because we have a fraction, we need the quotient rule also. So let me copy and bring that over. In conjunction with both the chain and power rules. Now, use the power rule first by moving the original exponent 8 to the front. And 1 is understood to be in front of the fraction. So 8 times 1 still gives us 8. Bring over g of x, or your what's in parentheses. Don't take the derivative yet. Times now the derivative of your fraction. Now this part here, we're going to work out down here, in which your numerator is your f and your denominator is g. So let's plug everything into our quotient rule. The derivative of f, or derivative of 3, times g of x, the original g, 7x minus 2, minus your original f of x, which is 3, and then times the derivative of g of x, or the derivative of 7x minus 2, And that's all over g of x quantity squared, or 7x minus 2 quantity squared. Now, going back to the front of the setup, the derivative of 3, with 3 being a constant, that's 0. So this entire first part is 0. Over here, the derivative of negative 2 is also 0. And finally, the derivative of 7x is just plain 7. So our derivative part here of the chain rule, this part of the chain rule, is negative 21 all over our denominator squared. Oh, I noticed I made a bad mistake at the beginning. When I used the power rule by moving the 8 to the front, I forgot to subtract 1 from the 8. So sorry for that omission. That should be to the 7th power. So just bring that down and put it in the front. And probably what my math lab would want you to do, just multiply the 8 times negative 21. So that would be negative 168 times 3 over 7x minus 2 to the 7th power. All over, actually, 7x minus 2 squared. Now, as far as I'm concerned, you can stop here. My math lab may go a little bit further by writing it this way. Negative 168 times 3 to the 7th power. And just use the product rule down here for exponents, not for derivatives. Because we got the same base, excuse me, because we have the same base down there as 7x minus 2, you can keep that 7x minus 2 and add the outer exponents. But as far as I'm concerned, you can stop there where I just boxed it in. So that's how you use the chain rule. Next, I want to go over the derivative rules for trig functions and for other special functions. And I can just go over them with you here on the screen. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Third one, the derivative of tangent x is secant squared x. The next one, the derivative of secant x is just secant times tangent. The derivative of cotangent is negative cosecant squared. And the last one, derivative of cosecant is negative cosecant cotangent. And down here under exponential derivatives, excuse me, The derivative of e to the x is the same. It's also e to the x. Let's use some of our derivative rules and incorporate some of this in here that we just learned. Let's see, given h of x is equal to x squared times sine of x, we need to find the first derivative. Since we have a product, then we must use the product rule. So here's our product rule for derivatives. X squared is our f of x, and sine of x is our g. Plugging everything into our product rule, the derivative of f of x, we're taking the derivative of x squared, times g of x, and the original g is just sine of x, plus the original f, or x squared, times the derivative of g, or a derivative of sine x. The front of the problem, the derivative of x squared using the power rule is just 2x times sine of x plus x squared times the derivative of sine of x is cosine x. And this is your final first derivative. Let's look at an example involving a fraction. Actually, before I try that one, let's look at an example involving the chain rule. To find the first derivative, we must use the chain rule. First up, find the derivative of sine of your function. So the derivative of sine of our function is cosine of our function, or cosine of 7x squared. This is the chain part of your chain rule times the derivative of your function in the parentheses. Use the power rule for derivatives by moving the 2 in front of your term and multiplying it by 7. So that gives us 14. And the last part of the power rule is you subtract 1 from the original exponent. So that gives us just plain x. So our final first derivative, when we move the 14x to the front, is 14x cosine of 7x squared. Let's look at an example now. Let's look at an example involving a fraction. And let me copy and paste our quotient rule. Okay, given this function, h of x equal to e to the x plus 2 all over tangent. And we need to find the first derivative. Because we're given a fraction, let's use the quotient rule, in which your numerator is your f of x and your denominator is your g of x. All right, so let's plug everything into our our quotient rule. The derivative of f means we'll take the derivative of e to the x plus 2 times the original g of x, or tangent x, minus the original f of x, or e to the x plus 2, times the derivative of g of x, or the derivative of tangent x, and that's all over the denominator squared, and that's actually tangent squared x. Moving back to the front of our setup, let's take the derivative. The derivative of e to the x is still e to the x, and the derivative of 2 is 0. So we have e to the x times tangent x. Right over here at the end, the derivative of tangent is secant squared x. And I'm doing two things at once here. We have a negative sign, so that makes it a negative secant squared x. And I'm going to distribute that negative secant squared x times everything in parentheses here. So that will give us negative e to the x secant squared x minus 2 secant squared x. And that's all over your denominator. And you can leave this as is. You don't have to substitute any formulas or change anything. The last thing I wanted to discuss with lesson 8 is, what if you have to take the derivative more than once? So far in this lecture, we've only found the first derivative. And that is noted by f, or whatever letter you're given, prime of x. But what if you had to find the derivative again, or the second derivative? This is called f double prime of x. So let's look at one example. We have f of x is negative 11x cubed plus 12x squared minus x plus 17. And we need to eventually find the second derivative. Quite simply, you're using the power rule several times. So for the first term, when we use the power rule for derivatives, we get negative 33x squared. Going down the line here, we got 24x. And remember, the derivative of like just plain x is, well, whatever, like if you had negative 2x, negative 3x, 99x, 101x, then your first derivative is just going to be the constant in front. For this problem, that's negative 1. And the derivative of 17 is 0. To find the second derivative, use the power rule again, and also the constant rule. The derivative of our first term would be negative 66x. Going down the line here, plus 24. And the derivative of negative 1 is 0. So in most cases, when you're asked to find the second derivative, and you're just taking the derivative twice, later on today or first thing tomorrow, when my video is done processing and there are no technical issues, I will share this video in Blackboard announcements.